Homework 1.7, Inequalities, video number 5. Homework due Saturday, May 16, 2020 at 11:59 p.m. In the previous videos, we talked about interval notation and linear inequalities. For the remaining videos in this series, we'll talk about other variations of inequalities. The bad news is we have to take a different approach when we go beyond linear. This one is quadratic because its highest power is x squared. But the good news is the technique that I'm going to show you for solving this non-linear inequality will work for any non-linear inequality. And in fact, the technique I'm going to show you now would also work for linear inequalities. It would be a little overkill, but it would get the job done. So let's try this one. Solve x squared minus 6x plus 8 is greater than or equal to 0. Now you might be thinking, do we have to get out the quadratic formula or factor? And the answer is eventually. But let's think about what would happen if we solved this. And at the end, I'm going to turn it into a sequence of steps to follow. So what if, instead of greater than or equal to, it just said equal to? Well, a couple of series of videos ago, we spent a lot of time solving quadratic equations. What if it said that? We could use the quadratic formula, but this guy will factor. Do you know what it will factor into? What two numbers add to give negative 6 but multiply to give positive 8? Answer in no particular order, negative 2 and negative 4. So if we were to set each factor equal to 0 and solve, we would get x equals 2 and x equals 4. But that's not what we want. That's what makes it equal to 0. We want to know what makes it greater than or equal to 0. Well, let's think about where these are on a number line. Remember, if you put more than one number on a number line, the key thing to do is to make sure that they're in order from least to greatest, left to right. So 2 would be to the left of 4. Well, we know what happens here. When x equals 2, it makes this equal to 0. And we know what happens here. When x equals 4, it makes this equal to 0. What we don't know what happens is to the left of 2, or between 2 and 4, or to the right of 4. I will tell you this. In each of these three intervals, the inequality will either be true or false. In other words, if I pick any number over here to the left of 2, it will make it true or it will make it false. It can't be a mixture of the two. Because if some numbers over here make it greater than 0 and some make it less than 0, then there would have to be one over here that makes it equal to 0, and the only places that make it equal to 0 are here or at 2 and 4. It has to do with a concept called continuity. If you take calculus, you will learn a lot about continuity. But I digress. If we can find the points on the number line that make it equal, then we can think about the number line being partitioned into smaller intervals. In this case, to the left of 2, between 2 and 4, and to the right of 4. And on each of those intervals, the inequality will either be true or false. So all we have to do is figure out which one it is. So let's pick a number to the left of 2. Give me any number less than 2. 1. Okay, let's pick x equals 1 over here. We want to see if 1 makes the original inequality true or false. So let's put 1 back into the original inequality. 1 squared minus 6 times 1 plus 8. And we want to know if that's greater than or equal to 0. Well, let's work out the left side. 1 squared is 1. 6 times 1 is 6. We still have the plus 8. Technically, these should all have question marks because we're asking, is that greater than or equal to 0? Well, if we combine the positives, 1 plus 8 is 9, and 9 minus 6 is 3. That wasn't supposed to happen, something else was supposed to happen. 1, 2. Sorry, folks, mental brain freeze. Oh, never mind. I was doing some number theory analysis and went off on a tangent, which is really bad because this is neither number theory nor trigonometry. Back back to the problem. 1 minus 6 plus 8 is 3, and we're asking if that's greater than or equal to 0. True or false? That is true. 3 is greater than or equal to 0. So what does that mean? That means that every number to the left of 2 is a solution. So I'm going to put a check above there. But now we have to check the other intervals that we created by partitioning the number line of the solutions of the equation. So we need to check between 2 and 4. And just for readability purposes, I'm going to change colors. The fact that this is in red is completely irrelevant. I need a number between 2 and 4. How about pi? No, I'm kidding. Although we could choose pi because it's between 2 and 4. But when you're picking a number, pick a convenient number. So 3 is good, but don't pick something like 2.718. So let's try 3 in the original inequality. Way back up here. We have 3 squared minus 6 times 3 plus 8, and we want to see if that's greater than or equal to 0. Well, 3 squared is 9. 6 times 3 is 18 plus 8, and we're looking to see if that's greater than or equal to 0. Well, 9 plus 8 is 17, and 17 minus 18 is negative 1. So is negative 1 greater than or equal to 0? No, that's false. And what that means is we do not want the interval that the 3 came from. So we don't want between 2 and 4. What about to the right of 4? Just to uncrowd this, I'm going to slide the 4 over a little bit. What about to the right of 4? Give me a number greater than 4. 5. And it really doesn't matter what number you pick. I could pick 5 or I could pick 5,000. As long as it's greater than 4, it's a good test value. So let's test this 5 back into the original inequality. 5 squared minus 6 times 5 plus 8. We're seeing if that is greater than or equal to 0. Well, 5 squared is 25. 6 times 5 is 30 plus 8. And we're still checking to see if that's greater than or equal to 0. If we combine our positives, 25 plus 8 is 33. 33 minus 30 is 3. Is greater than or equal to 0. That is also true. So we like that part of the number line. The numbers to the right of 4 make this inequality true. So, what's our solution? Well, we know everything over here to the left of 2 makes the inequality true because we took one test value and it worked. And we know everything to the right of 4 makes the inequality true because we picked one test value and it made it true. And remember that the numbers at which we partitioned the number line are the values that we got when we assumed it was an equality instead of an inequality. So let's see if we can write our solution. We want all the numbers less than 2. Now let's shade this in. We want all the numbers over here. Wait, do we want the 2? Where did the 2 come from? The 2 came from assuming it was equal. Does this inequality allow it to be equal? Yes. So we want the number that makes it equal. We want the 2. The 2 gets a bracket. And the same thing to the right side of 4. Everything to the right of 4 will make this inequality true. And we include the 4 because 4 was a solution to make it equal to 0. And our inequality says it's okay if it's equal. So it looks like our solution set has 2 disjoint intervals, so we're going to have to use a union symbol. The interval on the left is from negative infinity. Remember, infinity and negative infinity always get parentheses, comma 2, bracket on the 2 because 2 made it equal and it's okay if it's equal. And the right side of 4 is bracket 4 comma infinity with the parentheses, and since our solution has 2 disjoint intervals, we can join them together with the union symbol. So in an attempt to solve this, we kind of went through the process. So before I end this video and do one more where we work out another example, let's see if we can document the process that just happened. So we'll call this how to solve, frankly, any inequality. Now in the back of my mind, I know there are some other things that should be said, but for now it's going to be okay. Number 1, what do we do first? We pretended it said equals and then we solved. So change to an equation, or change to equals, and solve. So we found the numbers that made it equal to 0. But what did we do with those numbers? We took the number line and we plotted them on the number line, and imagine that cutting the number line into intervals. You may have heard me use the word partition. So we're going to say partition the number line at those solutions. So we partition the number line at 2 and 4. And what we're basically doing is cutting it into intervals. We just didn't write the intervals yet, but the left interval was negative infinity to 2, the middle interval was 2 to 4, and the right interval was 4 to infinity. But we don't have to write the intervals until the end. So what do we do after we cut the number line into 3 pieces, left, middle, and right? Then we picked a value from each interval, and you may have heard me call them a test value. Select one test value from each interval. Again, I'm thinking of the portions of the number line as intervals, even though I didn't write them explicitly. Negative infinity to 2, 2 to 4, 4 to infinity. Select one test value from each interval. So we selected 1, 3, and 5. And we checked those in the original inequality. So we're going to test each value in the original inequality. Emphasis on the word original. And after we tested them, we basically passed judgment on each interval. Interval number 1, you make the inequality true. Interval number 2, you made it false. Interval number 3, you made it true. So our fifth and final step is if a test value makes the inequality true, if a test value makes the inequality true, comma, its interval, because remember, the test value came from an interval. This one came from, test value of 1 came from the left interval. Test value of 5 came from the right interval. Test value of 3 came from the middle interval. If a test value makes the inequality true, its interval is part of the solution. Unfortunately, I ran out of room down there. So I'm going to put an asterisk on the word interval and define that asterisk up here. Sorry, I'm all over the place. Use parentheses if greater than or less than. Use brackets if greater than or equal to or less than or equal to. So the same protocol as before for deciding whether you use a bracket or a parentheses. Since this was greater than or equal to, we use brackets on the numbers. And remember, infinities always get parentheses. We're going to do one more polynomial inequality. It's not really going to be any different from the one you just saw. It's just another one to practice.